Okay, my clock says we're exactly on the hour, so we might as well make a start. So welcome everyone, good morning, good afternoon, good evening. Welcome to the One World Signal Processing Seminar Series, the European edition. My name is Christos Masouras, and I'm one of the co-organizers of this webinar series. And today we have the privilege to host Professor Deniz Gündüz for a talk on semantic communications. Very briefly, Deniz asked me to keep it very brief, his background. So Deniz received his bachelor's in Middle East Technical University in Ankara in 2002 and his PhD from New York University 2007. Since then, he's had a number of research and visiting positions, and now he's a professor in Imperial College London, where he leads the Information Processing and Communications Lab. He has many contributions in IEEE. He's an area editor of Transactions of Communications and editor for Transactions Wireless Communications. He's also served as a chair in a number of conferences, more recently in the London Symposium on Information Theory. He's received a number of awards. There are quite a few, too many to list, but most recent one, according to my records, is his Early Achievement Award from the Communication Society and the Information Theory. And he's held a starting grant of the ERC, which is one of the most prestigious European awards. His research, he's made seminal contributions in research, and most recently on deep learning applications for communications, and including semantic communications. That is going to be the topic of today's talk from Deniz. I'm about to give the floor to Deniz. I just want to remind everyone to please keep your microphones off while we're listening to the presentation, and please put any questions you have on the chat so we get the chance to ask them at the end. So without further ado, Deniz, over to you.
Thank you very much. Thank you, Christos, for the kind introduction. And also thank you for all the organizers for inviting me. It's really a pleasure to be among this really distinguished list of lined up speakers for this seminar series. And yeah, so I'm virtually joining from with the Imperial College background. And yeah, so I'll start with first maybe like trying to very briefly summarize what will be the main message of this talk. So it's on semantic and goal-oriented communications. As many of you are aware, probably these days these are quite popular terms. A lot of papers are appearing on this. Maybe one part of the talk, my goal is to try to a little bit explain at least what I understand from semantic and goal-oriented communications, as these are, in my opinion, not yet very well-defined concepts. And then I will go on to argue about basically if you want to design this kind of semantic or goal-oriented communication system, why these are essential, why we need to kind of look into this end-to-end design of such communication systems to basically meet the requirements of emerging edge intelligence applications. I will give quite many different applications and show examples where basically such design, so we can benefit from such a design. And finally, I will briefly talk about a new type of communication problem, new quote unquote. Again, I will explain what aspects of it new, which basically I will call the effective communications, or that's the part actually goal-oriented communications, hopefully, which will lead to some further research by some of you as well. Okay, so let me directly start with the talk, not actually before, of course, the acknowledgements. So these are some of our members, the Information Processing and Communications Lab, some of the former and current members, only those whose work I will, maybe briefly mention in this talk. And I also would like to, of course, this is a good opportunity to announce that we are hiring. There will be multiple postdoctoral researcher and PhD student positions available. So if any of the audience are interested in joining our lab, feel free to contact me through email. Okay, so now I can start. So one thing I would like to, maybe one of the main messages I would like to give about the semantic communications, as I said, I will try to first explain what I understand from that. But one of the things that I notice a lot, these days, a lot of papers, more kind of overview type of papers are appearing on this. Maybe I would say it's almost like there are more overview or survey papers than actually there are maybe more technical research papers on the topic these days. And one of the kind of claims that I commonly observe is that that the semantic communication is something that goes beyond standard like Shannon information theory. So we need we need to go beyond Shannon theory, and we need to come up with a new maybe approach to communications, which basically I will argue that this is true maybe to some limited extent, and very briefly, from my point of view, semantic communications can be understood very well in the context of joint source channel coding. And actually, many people would be surprised. Many people that know me might be surprised that I kind of use this semantic communications because from the very beginning, I always thought that this is more or less joint source channel coding. At least from the way our community mostly looks at this problem. But of course, now that this terminology is getting more popular, so I decided to follow suit. Okay, so of course one of the main reasons why people think that the semantic communication is beyond Shannon information theory is actually this statement from this paragraph from Shannon's mathematical theory of communication, where he basically explains the fundamental problem of communications, which is that of reproducing at one point either exactly or approximately a message selected at another point. And then he continues on to say that basically frequently the messages have meaning, that is, they refer to or correlated according to some system with certain physical or conceptual entities. And he explicitly states that these semantic aspects of communication are irrelevant to the engineering problem. So this led to, of course, not very surprisingly, to claim that Shannon theory does not deal with semantics. And basically, the first question I would like to ask is if that is really the case. And then Shannon, actually Weaver in the mathematical theory of communication wrote the paper accompanying Shannon's technical results, technical paper. And here, he classifies the communication problems into 3 levels. And here, level A is the technical problem, which is basically what stated by Shannon, how accurately the symbols of communication can be transmitted. And then he went on to say that level B is the semantic problem. So here the goal is to convey the desired meaning. And the level C is, how effectively does the received meaning affect the conduct in the desired way. So this is the effectiveness problem. So again, this is further evidence that Shannon information theory does not deal with this semantic aspect. But this, first, I would like to emphasize that, so I'm not going to go into details of semantics, which is a much kind of deeper concept and I would say, less understood. And in general, semantics deals with meaning. And many people have tried to come up with mathematical, so it's almost kind of borders philosophy, and there are lots of mathematical theories attempting to explain semantics, foremost the one by Carnap and Bar Hillel, and many others from also more communication perspective. And so the basic idea in most of at least for semantic communications, most of the papers that are appearing in recently in our community. So the goal is, the idea is that here we want to communicate some information source, typically, like some text is used. And the goal at the receiver is to reconstruct somehow the meaning, right? So not exactly word by word, maybe the text, but some sentence that kind of conveys the same meaning. Now, the assumption basically, as I said, the assumption here is that Shannon theory deals with, kind of exact reconstruction, but indeed that's not the case. So in Shannon theory, an important component of Shannon theory is the rate distortion theory, which was exposed by Shannon first time in his much lesser known 1959 paper. So as you know, in the 1949 paper, Shannon talked about source coding, but it was lossless compression. So he was showing that basically showed entropy as the limit of data compression. But in the 59 paper, he talks about actually we don't always need to reconstruct the source exactly. So we can introduce some distortion. So he gave these are actually figures from the paper. And for example, we can introduce some distortion or cost to reconstructing certain messages as different messages. And basically he developed the whole rate distortion theory. What is the fundamental limit of compression if we allow some inexact reconstruction? So in that sense, I would like to clarify that Shannon theory does not require exact reconstruction of messages. Channel coding theory does. And for example, in the very extreme, which is used a lot about to explain what is semantic communication. For example, if you want to transmit this image, rather than transmitting this image as pixel by pixel reproduction of this original image, we can transmit the semantic content of this image. For example, we can say there's a bicycle in front of some green trees, and one would reconstruct something like this, and this would still be a reconstruction, but basically we are now introducing a much more complex and involved reconstruction measure. So we are measuring the reconstruction through a different type of a semantic quality metric. Okay, so now I would like to kind of put into context, even though this is very familiar with many of you. I would like to briefly talk about this fundamental information theoretic formulation of the communication problem. So we have this source SM. So these are samples from some IID samples, let's say from the distribution PS. And the transmitter, the encoder, wants to transmit these samples over a noisy channel from Xn to Yn using the channel n times. And this is a memoryless channel with a given conditional distribution. And the decoder wants to reconstruct these samples. And now, in the case of lossy reconstruction, we have some distortion measure. So this is given to us. And in the standard, let's say, a memoryless Shannon theory, these are additive distortion measures. So the distortion between two m-length sequences is the average of symbol by distortions measured by this distortion measure D. And in this case, so the goal is to find the source channel rates n over m. So how many times we need to use the channel on average per source sample to acquire kind of a reconstruction of this source average reconstruction quality of capital D. So then, that will be the distortion pair RD, and for a given D, we might, for example, try to find the minimum R, minimum source channel rate. And again, for example, if for a non-trivial kind of channel with a non-zero capacity, this says that we can transmit any source with any desired distortion as long as we are allowed to use the channel as many times as we like. Now, this is, I say, basically the fundamental problem of information theory, because this generalizes both a source coding theorem, source coding problem, and also the channel coding problem. Because if we fix the channel to be a error-free bit pipe, this becomes the source coding problem. If we let the source to be binary samples, IID samples, equally likely, that becomes the channel coding problem. Okay, and Shannon also went on to prove this is a very fundamental theorem, basically, which known as the separation theorem, which shows that you can actually divide this problem into these two source coding and channel coding problems without loss of optimality, meaning that it's optimal to first compress this source into bits, get rid of the redundancy, and then send these compressed bits over the channel, adding optimal number of redundancy bits using the optimal channel capacity achieving channel codes. So this is very important, because this basically led to kind of this separating this problem into two and dealing with these two problems separately without at least asymptotic loss of optimality. So this is, I'm saying asymptotic loss of optimality because this holds only in the limit of source samples and the channel uses going to infinity. and also under this, like memoryless source and channel assumptions. I mean, that can be extended beyond that, but again, under certain ergodistic assumptions. Now, this has been, this has been very instrumental in the design of communication systems. Like we basically have this, take care of compression in the upper layers, and then the lower layers generally ignore, what the bits given to them by the upper layers come from. And the sole purpose of the physical layer, for example, is to convey these bits reliably over the channel. So now the questions are, of course, first of all, as I said, so this is an asymptotic result. So in practice, when we have finite sources, let's say we want to send an image over a channel, especially in cases, like where this number of channel users or the size of the source sample source sequence are limited, we will be further and further away from the optimality of separation. So there will be something to gain by looking at this problem in an end-to-end fashion. Second, in like 6G future systems, more and more, we will be dealing with machine type of communication. So these communications will be among, like autonomous cars, robots, or different devices, sensors, etc. And it's rare that these devices, for example, that a robot will be really like to, like receive an image and reconstruct the image and look at it. So most probably in those cases, such a device will be doing some inferences on the image rather than, like reconstructing it for just purposes of seeing the image. And so in that case, the question is, so is separation is still optimal? Are we still close to optimality in practice? And what better things we can do? And another thing is, like what I will argue is that actually basically this latency cost of modularity will be too much for many ML applications, machine learning applications, where the latency really becomes essential. Okay, so I will go into, like more details of these. So so far, so what we have said, so the separation is optimal, but maybe in some systems, even, like the separation is optimal, but maybe we want to actually do things faster, or easier. So use different type of coding schemes might be beneficial. So then so I pose this question: can we beat the Shannon limit? So obviously the answer is no, but we can actually meet the Shannon limit using something very different. And so this is actually a well-known aspect of source channel coding. Basically here, what's happening, what I'm trying to say is that, so you have a source normally, so the Shannon separation theorem says that take many samples of the source, IID samples, compress them using, vector quantization, whatever rate distortion optimal, near optimal scheme, then use channel coding using the channel many times using long block channel codes. But as opposed to that, sometimes it's possible that actually you can simply send the source samples one by one over the channel and just use, no coding at all, and just use estimation at the receiver. And it turns out that this is actually exactly optimal in Shannon theoretic sense. So you don't need to do any of those coding. And this is typically attributed in like in most papers. Most of the times in most recent kind of generalizations of this result was Gaspar, Vetterli, and Rimoldi, but much earlier than that, in early 60s, studied by Goblik, who showed basically this is the case if you're transmitting Gaussian source over an edited white Gaussian channel, and then analog modulation is actually optimal. And but what is less known is actually this was also shown by Shannon again in that 59 paper. So Shannon in both cases, actually in both papers, didn't only look at the source coding and the channel coding problem, but he also proved the joint source channel, looked at the joint source channel coding problem, and proved this optimality of separation. But he went on in this paper to show that actually, even though separation is optimal, there will be cases where when the source and the channel statistics match, this uncoded transmission will be optimal. So this statement is from the paper that any symmetric binary channel will have one point that can be attained exactly by means of straight transmission. So this is basically uncoded transmission. So this is obviously some statistical peculiarity, you can say. And actually I spent like quite a bit of my PhD and later years to look into this for different types of source statistics, channel statistics, when this would happen, this optimality. But what this says that, there is this optimality, but what kind of maybe less obvious is that this also says that even when it's not optimal, there might be cases that doing this type of coding might be closer to optimality and might be good enough. And also note that in many cases, in practical cases, when transmitting, for example, images or videos over channels, we are not operating on the Shannon bound anyway, right? So it's not like we have the rate distortion optimal compression scheme. So it's not clear, if this type of coding scheme would be much worse off. So the goal here is to transmit some, let's say, an image over a channel, a noisy channel, and what we have, like so far. So this is now I'm not able to go back. Maybe this is because okay, now it's working. Okay, so far we are saying that so this we have this joint source channel coding problem. Let's say we want to transmit an image. An image has a lot of semantic information, and maybe we want to reconstruct it with some perceptional reconstruction, some involved quality metric. So in general, we have this optimality of separation, but and this type of complex semantic type of reconstruction metrics will require to do something, like to go beyond, like standard techniques. And actually one thing we know that has been very successful for, understanding the semantics of sources, especially from a statistical point of view, is using, machine learning tools, recently deep learning, right? So to understand, to better compress or better understand for different tasks, semantic information in complex sources. And here now we want to also say, so we have the second layer of like difficulty, that we are saying that okay, we want to do some sort of joint end-to-end design of the communication system, but this is much more complex than like purely looking at the compression problem or the channel coding problem. And of course, like not surprisingly, the idea is to use like neural networks now to do both. So in a way, now what we want to do is to design the communication system end to end. And so we have the image and then directly map it to the channel inputs using a neural network, and the receiver a paired neural network decoder that directly reconstructs. So now what we expect is that this neural network will not only understand the semantic content of this source to allow the best reconstruction, but we'll also understand how it should be mapped into the channel signal. And that's what we did a few years ago, and it gave actually like quite impressive results. So here what we are comparing, like for this well-known Kodak data set, the transmission of images over AWGN channels using a neural network autoencoder type of transmission compared to state-of-the-art, let's say BPG plus LDP BPG compression combined with LDP, almost basically channel capacity achieving channel coding. And you can see that we are very close in terms of performance to this. And what I would like to emphasize is that this is so both BPG and LDPC are decades long results of decades long research efforts, maybe billions of dollars of spent money. Whereas what we achieve here, this green curve, is a result of simply several hours of neural network training. And not only so, this is for a fixed kind of compression rate, so channel uses per source sample. And it turns out actually if you go into the extremes, for example, very low SNRs or very low channel bandwidths, you actually tend to get better, compared to the improve upon the state-of-the-art digital schemes. So, and this is quite actually a powerful tool, because as I said, before I was showing like PSNR results comparison in terms of the reconstruction of the images, but you can also use MSSSIM type more kind of perceptual aligned reconstruction metrics where BPG or JPEG or whatever, so they cannot be adapted to like the reconstruction measure. But whereas like you can train the neural network as long as you have a differentiable performance measure. And here, for example, if we train with this MSSSIM metric as the objective function, we get even more like significant improvement compared to BPG plus LDPC. So here again, basically shows that this type of this end-to-end scheme not only learns the semantics within the image in a way, but also learns to how to transmit, map it to the channel input space, and then later from the channel output space directly back to the image. And again, you can also, like focus on to a certain domain adaptation. For example, if you're transmitting only satellite images, you will do even better, right? Because you will this type of scheme will learn actually the statistics of this type of particular source. Now, another advantage of this scheme is that it's naturally analog-like. What I mean, like here, for example, if you see these gray curves, the digital schemes, where basically you design an BPG plus LDPC scheme, but when the channel quality goes below what you trained for, what you designed your code for, you will lose everything, right? So the channel coding has this type of cliff effect. You will not be able to decode. Whereas this scheme that, like this neural network based coding scheme has a graceful degradation. So if the channel goes bad, it gracefully degrades. And also, it's possible to have actually, if you have channel state information, then it's possible actually to also even have channel SNR adaptation. And of course, this graceful degradation property naturally allows much better performance. For example, if you're communicating over a Rayleigh fading channel, and if there's no channel state information either at the transmitter or the receiver, then this gives a natural kind of adaptation. And of course, this also extends to the case when you are transmitting to multiple receivers. For example, if you're broadcasting, so it will this type of scheme will naturally allow each receiver to reconstruct the image, the quality that its own channel allows. So it's a very nice property. Okay, so here I also give some examples, like here compared to, the original image on the left column, BPG plus LDPC results on the column in the middle, and here the deep JSCC results obtained through this neural network-based encoder-decoder schemes on the right. And you can actually see, this BPG gave some blurry reconstruction of these high-resolution images, whereas the deep JSCC scheme is quite crisp, clear images. And these are for, like 24 times compression in terms of channel uses per source sample. Okay, so this is, like basically what I would like to say is like one can treat this as a semantic communication system. Here, the goal is to somehow reconstruct the image with some perceptual based quality metric. And of course it can be, I will show that later, we can use other reconstruction metrics as well. So there basically we use this kind of deterministic autoencoder type of scheme. But later we also looked at, more recently looked at this wiretap channel type of setting. So here the idea, like the Alice wants to communicate this image, let's say, to Bob, and in the meantime, Eve is listening to this channel, so it receives some noisy version of Alice's transmitted code word. And from that, Eve maybe doesn't want to reconstruct the image, but wants to get some sensitive information about the image, for example, color and thickness of these digits, right? So obviously it can be, like any kind of latent private information in general. So now in this case, we trained use the generative model. So why we use the generative model? Because this, for example, a variation of autoencoder here, because that will give a stochastic encoder. And as we know that, like for general wiretap channels, using a stochastic encoder benefits because it kind of introduces extra randomness and confusion for the eavesdropper. And using that, basically we were successfully able to like transmit this here, some examples of the images on the top, and at the bottom basically the image reconstructed by the legitimate receiver Bob, and below, even though Eve doesn't really want to reconstruct, but we basically just to kind of visually illustrate, we also looked at, of course, the accuracy of Eve trying to infer this color and thickness information, but here we also allow it kind of to reconstruct, and you can see that actually the Eve is mostly like confused about both the color and the thickness of these digits. And here basically what's happening is that Alice successfully kind of embeds this information, this color and thickness information, into the kind of more noisy parts that the Eve cannot recover, so that Bob can recover. As you can see, Bob actually can get the color information, but Eve cannot. So I would like to emphasize that this, this is not only a kind of a new type of joint source channel coding scheme, but this also is quite a general kind of problem, because it generalizes not only point-to-point, joint source channel coding problem, but if we assume, for example, this channel to be an ideal channel, where basically whatever is transmitted here is received by both Bob and Eve. So this reduces to the well-known privacy funnel problem, because here basically what's happening is that Alice will be releasing some version of its source to Bob and Eve, which are now basically the same person in a way, same legitimate receiver of this revealed information. And Alice wants Bob to be, for example, able to reconstruct the image or to get something out of the image. It could be also, maximize the mutual information between this, whatever revealed to Bob and the source, while keeping this latent private information as, hidden as possible. So this is this kind of famous privacy funnel problem, or the privacy utility trade-off. So now here basically that is generalized into a wiretap channel setting, and we also use this generate this kind of stochastic encoding scheme. And of course, in general, this could also be used as, like here we are assuming that this generative parameters of the generative decoder. So basically, the Alice is giving some parameters to the Bob, and the Bob uses this to generate randomly, sample randomly from a distribution. So if, for example, if Bob was some random receiver, which doesn't actually was some oblivious receiver, we could also, first convey these parameters, this reconstruction parameters to Bob, and then allow this Bob to reconstruct the image. So this would be considered also maybe as a more general kind of semantic communication scheme. Okay, so I argued for this, semantic communication in the context of more image reconstruction, but obviously, that source can be anything. So, and as I said initially, there are a lot of works now considering text and speech. So, because in that case, it's even more clear, for example, reconstructing a text, not exactly, but giving the same meaning. So would be conveying the semantic information in a way. And of course, again, going back to more the, analysis of semantic analysis of text, speech, etc. The most kind of powerful tools these days are using, machine learning tools for natural language processing. So here, we can directly basically use some of those techniques for semantic communication of such sources, combined with this, joint source channel coding approach. So now basically we will design. So in these papers, basically. And such encoder decoder pairs are trained in an end-to-end fashion. Okay, so I hope here I kind of I was able to convince that at least many of the the semantic communication problems are actually just joint source channel coding problems with maybe potentially a very involved complex reconstruction measure. And a lot of people also look at this remote inference problems, right? So here the issue is that, as I mentioned, typically in many kind of emerging applications, the sensors, autonomous devices, etc., maybe they don't care about reconstructing the underlying image or other sources, but they want to make some inferences. So now the goal is, this encoder observes some image, wants to transmit to the decoder, and then we only care decoder to make and say that whether it's a dog or a cat. Now the question is separation theoretically optimal? What are the practical approaches? And is this, somehow different from this type of problems we had before, where we were trying to reconstruct the source signal? And actually, I've seen some papers classifying, saying for some reason, if you want to reconstruct the image, it's joint source channel coding problem. But if you want to do some inference, it's a semantic communication problem. Okay, so if we, so the first thing I would like to say is that, in my opinion, this is still a joint source channel coding problem. So here, basically, what's happening is that, so we are assuming that this image that we have has some underlying latent property, right, being a dog or a cat. So we can model that as another random variable. And instead of observing that random variable, we are actually observing its image kind of reflection, right? And what we want to convey is that underlying latent random variable. And this is known as remote rate distortion problem if it's a compression problem, or remote joint source channel coding problem if we have a noisy channel. So it's nothing, like different. It's just that now we are observing the source, a noisy version of the underlying source that we want to communicate. Okay. Okay. So now what we did first was, to come up with some theoretical formulation of this problem. So here, we said, okay, so we can look at this problem as a hypothesis testing problem. So let's say the observer has IID samples from this U. We want to transmit over the channel, and the detector wants to say if it's this, like hypothesis 0 or hypothesis 1, in a way it's a dog or a cat. And we want to look at the type 2 error exponent under a constraint on the type 1 error exponent on this binary hypothesis test. And here it's not difficult to show that actually in this case, as separation is optimal in the sense that what is best is that the observer, which has access to all the clean samples, should do the hypothesis test, should make the decision whether it is like dog or a cat, or null or the alternate hypothesis, and just send that binary information over the channel, for which the error probability will be given by the channel error exponent. And so basically this can be proven. So we proved this in this ISIT paper. But then more interesting case is when the decision cannot be made locally by the observer, and that happens if the detector has some side information, and our goal is to actually make an hypothesis on the joint distribution of what the observer observes and what the detector observes. So now the observer doesn't have this access to side information, so it cannot make that decision. It needs to send some feature of what it observes over the channel to allow the detector to make the right decision. And it turns out that this is quite interesting result, I would say, that we were able to show this, to quantify this in a single letter information theoretic form, the optimal type 2 error exponent. And when there is, in the case of testing against conditional independence, and it turns out actually in this case that some sort of separation is optimal. So in the sense that, what matters is only the channel capacity. But if you are testing anything but conditional independence, that's not the case. So we actually have some example where separation is suboptimal. So this is quite interesting. For general inference, we need to look at the end-to-end problem. And we thought, okay, so what is the kind of practical ramifications of this? What would be the practical problem that corresponds to this? And it's this image retrieval problem. So what's happening here is that this camera observes an image and wants to transmit over the wireless channel to the receiver, edge server, which has a database of images of the people taken from different cameras, different angles. And the goal is to say whether this image is, matches to one of the people in the database. Now, note that unlike that classification problem saying it's a human or not or whatever, now the camera again cannot make the decision locally because it doesn't have access to this database, and it should just send some features of the image to make the best decision. Here we took two approaches. So the first is the fully digital approach. Here the goal, basically the solution is going to be to do task-oriented compression. So basically you compress the images for the retrieval purposes. So we designed this kind of neural network-based compression scheme and then transmitted this over the channel using, let's say, capacity-achieving channel codes. So this is a separation-based approach, but still for the compression, we are using this kind of this task-oriented aspect. We are not just sending the image because the receiver doesn't care about reconstructing the image. The alternative approach is the kind of corresponds to this deep JSCC. Here, we design end-to-end, basically how should we map these features to the channel such that, this will allow the retrieval the best. And not surprisingly, this performs much better. So you can see this blue and the orange are two types of, joint transmission schemes. They actually almost match the baseline kind of perfect, everything is available at the receiver benchmark, this dashed curve, even at very, like 5 dB channel SNR. Whereas this, the separation-based approach is all, is quite below, is a significant gap. This is in terms of top 1 accuracy. So how, accurately we actually find the right matching images. And if we were to transmit the image and then do the retrieval at the receiver, that actually that plot doesn't even fit into this figure. So it's much worse. So this is what I meant by basically this kind of strictly separate approach that we use in a way in conventional systems today, use the standard, like separation compression and then doing everything at the receiver kind of approach, and the separate the channel coding approach is not going to meet the requirements of many edge machine learning applications. Okay, so I would like to now change a little bit the problem. So before in all this, problems, we were saying that, okay, there's some sort of database, some problem specific and some random channel, etc. And then we train some neural networks and test them for the test data set. But in many cases these days, we are training, different neural networks that are, location-based or, time-based, etc. And we need to convey these neural networks over the channel. So this will require, for example, a car, goes into some base station, some cellular coverage area, and need to download neural networks, for example, to do millimeter wave beam alignments that are specific to this cell. So this will require, such applications will require communication of neural networks. So this is, I would say, it will become a major research problem. And again, we looked at this in an end-to-end fashion, so also modeling this as a joint source channel coding problem, but this is very different because note that here, the source is the neural network, so we want to receive at the receiver, but we don't care about reconstructing the neural network. We care about reconstructing something that will give the best accuracy. So this is again a very different type of a semantic type of measure at the receiver. So again, we basically show that you can do actually this type of analog transmission of the neural network parameters together with some pruning, etc. type of compression schemes to convey this neural networks parameters best in a best manner. Okay, so now I will go into, so far these were about, distributed inference problems, right? So we were doing some, classification, regression, whatever, some inference task. But there is also a major problem in machine learning is the training. And in many cases, we know, especially in edge applications, we need to do the training in a distributed fashion. And a lot of people have been looking into, things like federated learning, etc. So for this, in federated learning scenario, for example, these devices have their local data sets and they want to train a joint model. So the problem, the way it's done is that, each device trains a local model and then they send these local models to the parameter server, which somehow aggregates them. And this aggregation is done by averaging them. So basically when we looked at this problem, we basically said that this is nothing but a distributed communication problem, but with a distributed computation problem. So in a way, it's a joint source channel computation problem, right? So we have these local, model updates or models, whatever we want to convey, but we don't want to convey them individually. We want the parameter server to reconstruct the average of them. So this is, again, I argue that this is just a different distortion measure. So now the distortion is defined on how good the quality of, of whatever the reconstruction at the parameter server with respect to the real, the average value. So, and actually this is, again, so it's a joint source channel coding problem in a multi-user setting. And people have known that this separation in this case also fails. And typically they refer to the, Kovar-El-Gamal-Salehi paper, which looks at multiple access channel with correlated sources. But again, I would like to point out that actually this was also studied by Shannon in a two-way communication channel. So he showed again in a two-way communication channel that separation fails, and by just sending uncoded transmission, you can actually get the better performance. So here, under this this setting, we introduced this over-the-air computation. So the idea here is that, again, so these are our local gradients at the devices that we want to average at the parameter server over a wireless multiple access channel. Now, so instead of compressing and transmitting each one individually over, somehow some orthogonal scheme, we basically send them in an analog fashion and the channel directly averages them. So the channel does the computation, and hence this is called over-the-air computation. And this was already kind of people have been looking at this type of Goldenbaum et al. Several papers some years ago for just for the purpose of some computations. So we apply this, but here our paper had another contribution, because basically here these neural networks, these gradients, of the neural networks are huge vectors, typically, hundreds of millions of parameters. So if you do, like this uncoded transmission over the air, even though you superpose them, you don't give orthogonal resources, it will still require a huge bandwidth. And how would you reduce this bandwidth? Because in digital schemes, you can compress, you can reduce. So digital schemes allow compression, but analog schemes, it's not clear how they would allow you to compress. So this is what we did. So we said, basically, you can use some random projection, kind of similar to, compressive sensing type or sketching type of applications. So we project them into a lower dimension and use some, approximate message passing type of decoding. And it turns out this actually helps, and you can get actually still very good performance, and with this, significant compression. So then, of course, this has been extended to, like if this, what happens if these are wireless channels, then in that case, you need channel state information and channel inversion, such that, what each device is sending aligns at the receiver at the same level. Otherwise, different channel gains, some kind of components will be, amplified, some will be attenuated. So that will introduce bias in the learned model. So we don't want that. So we need to use this kind of channel immersion type of schemes. So again, it works. But what we did also, that even if you don't have channel state information, which might be challenging in practice, you can use actually multiple antennas at the receiver, and that would allow you actually to achieve still a good performance. So that's kind of, using this channel hardening effect to do the over-the-air computation. Okay, so again, just very kind of brief note here is that, this assumes perfect alignment, of course, across all these transmitters, but we also looked at in this recent paper, even if the alignment is not perfect, you can do some schemes, but of course, there will be some loss. So finally, in the last, a few minutes, I would like to talk about this new type of problems that I will propose as this level C, corresponding to level C of the Weaver and Shannon's classification, effectiveness problem. So what they were saying was that how effectively does the receive meaning affect the conduct in the desired way? So how do you, change the conduct of the receiver by sending a certain communication symbol? So here, so basically, if the receiver does some action, if you look at this as a kind of a one-shot case, again, so I want the receiver to do some action, I send some signal, and then I can measure how accurate, how good this action of the receiver. This would, again, boil down to a joint source channel coding problem, right? It's just basically the distortion measure will be on the actions taken by the receiver. So it's not going to be fundamentally different. When it will be different is if these actions are taken in an iterative manner over time. So for this, like we modeled this remote Markov decision problem. So what do we mean? So in standard Markov decision problems, you have an agent taking actions and interacting with the environment and collecting reward and trying to kind of maximize that average reward over time. So we take any arbitrary Markov decision problem and then divided the agent into two. So now we have a controller agent, which observes the state and the reward, and an action taking agent, like a robot, which just takes the actions but doesn't see the reward or the state. And now this controller needs to communicate to the agent over a wireless channel. So here the controller needs to control the agents to maximize this reward, but now there's this additional noise introduced by the channel. And now the goal over the channel is not just one shot. We don't get some reward every time, but we get reward every time. But what we are trying to optimize is this kind of how we actually really affect the overall goal of the agent. So whether, for example, the agent eventually gets the target, or maximizes his discounted long-term reward. So we looked at this problem on the simple grid world type of setting, and obviously, if you do separate, you solve the separate the reinforcement learning problem, and then map it into some channel code. Here we use this 7/4 Hamming code. So you lose performance. It takes longer, average number of steps, whereas this joint learning is much faster on average, because basically what it does, it learns to map the actions that we communicate to the agent in a way that, even if you make a mistake, for example, in the separation-based scheme, if you make an error over the channel, so here the agent, instead of getting closer to the target, it might end up somewhere, like much worse off. So might get further away from the target. Whereas if you do the kind of end-to-end learning here, with the same type of channel error, you will actually getting, instead of, getting to the here closer, you will get still, like somewhere closer to the target. So this will, train a much better kind of communication scheme. We later also extended to multiple agents, and it turns out actually that this end-to-end, learned communication scheme through reinforcement learning actually learns to somehow divide the communication resources among the agents. So here we see basically that the communication to the agents and their actions, here you see that they are like completely so in the time division manner. So if you just communicate part of one part to one agent and the another time to the another agent, you will see that it's kind of completely orthogonal, right? So each agent only uses some part of the time, part of the message. But if you train end to end, it turns out that somehow agents learn to exploit the whole available resources. So in a way, it learns some sort of superposition transmission scheme. So finally, this context awareness. So we know that in humans, like we have this kind of context awareness. So the same message can mean something completely different in a different context, but we naturally understand that, and then we understand the semantic of this, the meaning of this message. So to model this, we looked at again in this setting of effective communication. So again, here, like we want to send the agent, like to some target or, like to some objective over an iterative fashion. And now the question is like, what should we transmit? So now we are assuming the agent knows its state. So it knows when it is, but it doesn't know where the target is. So there are two possible options. You can either send the target location and hope that the agent will eventually figure out how to get there, or you can send the action as before. You can just tell the agent, how to go. Now, it turns out that actually the optimal thing to do is to start by sending the target location. And when the agent gets close enough, you start sending the action. So in a way, now, just based on purely the context, which is the kind of the state of the world, the agent, using the exact same message, does something completely different. And then they learn this through the training process. So this is quite interesting. Basically, it's not just, like you send a different message based on the location, which is obvious, but here you completely change the code book, the communication scheme, depending on the context. Okay, so I think I'm running out of time. So I would like to conclude here. So very briefly, I hope, like I tried to, I gave some a little bit better understanding of what semantic communications or goal-oriented communications could be, understood as in the context of, this emerging wireless communications applications. Again, I didn't, like mention much, or I don't maybe even know much about, what semantic is, but I try to explain what, semantic communication could be understood as and is actually used as in most research these days. And yeah, so the practical codes, I looked into some, information theoretic aspects, also some learning theoretic aspects, but in general, practical code design and implementation for these problems are widely open. There are lots of open problems, and machine learning is definitely a valuable tool to solve these problems. And finally, I propose this kind of a way of understanding the effectiveness problem. So I would like to also, finish by announcing this new special issue, JSEC special issue, which will be about basically this semantic and task-oriented communications. The call for papers will be out soon. And with this, yeah, I would like to stop here and see if there are any questions.
Okay, many thanks, Deniz, for this very fundamental and interesting talk. It was also very dense. I think you gave us content of 2 hours, maybe, and 1 hour's duration. So a lot of us are still digesting, I think.
Lots of compression.
Yeah. So we have one question, which I'm trying to understand myself a little bit. I don't know if you can see it. So,
yeah, in the chat, channel sparsity, low rank, roots, small angles, spread in angular domain, etc. Pros, cons. I'm not able to understand.
So yeah, I guess it relates to how you can treat with your framework, these 4 problems. So small angle spread in angular domains.
And the less training overhead, less accuracy.
Yeah, and the trade-offs between training and accuracy, I guess.
I mean, I didn't really talk about, this particular problem, so I'm not sure, like where it's kind of really refers to. But I mean, I don't know. In general, of course, these machine learning approaches, I think, one of the common questions always, there's this training kind of overhead. I mean, yes, that is definitely there, but in many cases, especially if you have a good model of the channel, which is generally the assumption in model-based solutions as well, then the expectation is that will be good enough in practice, and you'll do the training offline and won't need to do, or you might do some additional online learning type of extra learning in the time of testing, and hopefully that will be limited because you had a prior good model, good enough model, let's say. I don't know if that answered the question, because I'm not sure I understood the question.
I mean, I had a similar thought while we're waiting for any more questions. Maybe I'll ask you some naive ones, not being an expert in the area. So there are some assumptions on some idealistic assumptions, right, on the channel, or maybe on the implementation and what you can transmit. Maybe I wonder whether some imperfections in hardware or anything like that can be modeled into these this framework that you have. To make these more practical, let's say, maybe some constraints in what you can transmit, because I guess you assume you can transmit anything, and then you choose how to split the coding and so on.
Yes, I think, I mean, this is definitely, like making these things, bringing these things closer to reality. I mean, all these things have to be put into the, picture. I completely agree. And yes, at the moment, for example, the ones that I was presenting were all about, yes, you have an AWGN channel, you can transmit anything, and, just edit the white Gaussian noise. We have now a new paper which will be, available soon. For example, we limit ourselves to some constellation, let's say. So that's kind of one thing, right? And then you can also look at the PAPR, like all sorts of, I mean, you can introduce all this, right? So, and then you will of course need to introduce these as some, part of your objective loss function. And a good question is, of course, then, how much of these gains are still going to be there is a valid and definitely an important question to look at. So yeah, I don't have a general answer, but they are definitely possible to be made part of the problem. The approach doesn't exclude this. It's just a matter of time, I guess. That's and I'm sure some of the audience have looked at some of these problems.
Yeah, I think that's an interesting way to go. And also, I mean, you seem to, at least most of what you presented was about distortion metrics and, least squares kind of metrics. And again, I wonder whether you can, I mean, you talk about trade-offs with latency, complexity, learning, memory. Maybe these could be introduced with some mathematical expression there, right? So not trying to minimize the bottom line MSC, but minimize some sort of trade-off or a weighted.
Absolutely, that's what I was trying to say as part of the loss function, right? So it can be introduced like additional kind of weighted, like parameter, or you can look at the Pareto, surface. Yeah, absolutely.
Yeah, that's very interesting, I think. Yeah. The other small question I had, maybe that's something I missed, is whether, so you talked about the scenario where you had these MTC, so machine type communications, where you don't want to reconstruct, but you want to do your bottom line inference. And I wonder whether you've looked at, or you're aware of somebody who's looking at the effects of small packets in the capacity and what you can achieve there, and whether that would change your framework.
Sorry, the small packets?
So the effects of the small packets, the small packets when you don't have, let's say, codes of infinite length will change your capacity.
Yeah, so the way we are looking at it actually is like that. So basically we say that, okay, so I have an image, and I will, let's say I'm given a certain number of channel uses, and typically this is small. So I can't remember now, maybe it's actually level of 125 symbols. So it's a very short packets actually. And then we want to do the class, because actually if it is very long, then you can, then it becomes easier. So and then even maybe separation based schemes can actually do quite well. So in that sense, actually, we are looking at the very short block length regime typically, and those are the regimes that this gains by doing end-to-end learning is much more significant.
Okay, great. That answers that. So I think we don't have. I'm not seeing any questions.
I see on the chat.
Okay.
Yeah. So should I answer? Do we have time, or how do we
let's give it another 5 minutes. Yeah.
Okay.
To see what we can answer.
Yeah. So Lefteris. So first, hi to you. So he's asking. Yeah. So the multiple users and permutation ambiguity. Good question. So this is. I mean, in our case, we are just, like training this kind of as a, through the reinforcement learning framework. I'm guessing, like somehow they learn, like which resources, somehow which symbols are aligned. So that was one reason we looked at that correlation, basically which symbol correlates more with the actions of which agent. It turns out that they are all correlated. So as I was showing, so they are not like time. So it's for sure the scheme is not doing time division. But it's not clear, obviously, at this stage, actually, how they are understanding which is meant for them. It's a very good question. We should actually, I don't know how we can actually, quantify that, but something we will look at. For the detection classification problem, we need an external neural network for each classification task. That is correct. Does it mean future transmitters need a large database for storing all the parameters for the neural networks to be applied? That's a very good point. And that's a problem in general, I guess, for like using neural networks for anything. And yes, so the of course, the potential solutions for these is this kind of methods to compress neural networks to reduce their dimensionality, etc. But or like at least for some similar task, use this kind of transfer learning type of tools to maybe use one network for multiple tasks. But yes, that's an issue. I think will be general.
Yeah. Next one is from Marie Kobayashi.
Yeah.
Just to explain the PSNR and how that captures semantics.
Yeah. So actually, in general, I didn't say that captures semantics. I mean, it might capture. You might, because semantics is very like at least the way I understand it can be anything. But what I was more claiming was this SSIM type, structure similarity type of metrics would be considered as a more kind, because those are more kind of perceptually aligned, thought to be more capturing the perceived quality of images. But of course, one can also just do testing on humans and things like that, right? So you can ask people. There are some papers on that for more on the compression side. And try to quantify basically how good the reconstruction for people's from people's perspective, which would be much more semantic oriented.
There's a couple more coming in. I don't know, Deniz, do you have the time to stay a bit extra and
I can, yeah. I mean, since
okay, let's do that then.
For me, it's okay, but obviously, like people are free to naturally leave, but this will be recorded, so it's okay to kind of have that.
Yeah, that's would be good if we can.
Okay, so something similar? Should I read? Yeah.
Yeah. Go ahead.
Okay. So Jeremy is asking something be done in the framework fully decentralized learning where agents learn to communicate and each have their own task, or is the decentralized approach necessary? So this is a very, very good question, and it's something that we are actually looking at. And yeah, so how the training will be done, like how much it can be fully decentralized is open. And I think, yeah, that's a very, very good, good research direction. Sean Hong, thank you much.
3 questions.
Yeah.
So why can features be understood as semantic information while people cannot understand these pictures directly? Okay, that's a bit more general question.
Okay, so first of all, I'm not generally saying that features are semantics. Features are somehow capturing the semantics. So what you do with those features will be the semantics. Now, yeah. So the people cannot understand.
I mean, it depends on the task as well,
exactly.
Right? I mean, it's not the same.
That's true. And also, I don't know, like maybe in our brains also we are capturing some features. Maybe we don't understand them, right? So what is really happening inside so we are only understanding or think that we are understanding the reflection of the final product. And maybe that's similar to what's happening here.
Yeah, and I guess the semantic depends on what you're doing. It doesn't mean that something a human perceives is what is desired, right?
Exactly. Yeah. So I mean, yeah. So I think that's one of the messages that for me the semantics is basically anything any objective function could be understood as semantics. Again, obviously there's a semantic what it is, what is meaning, much more abstract. That's I don't like I'm not looking at that. I'm not blaming anything on that. And how can we combine JSCC with modulation? So here is actually, we are using modulation. We can basically, this would be completely OFDM modulation. What we are doing is that we are just allowing the IQ, like the components modulated over the channel to be arbitrary values, not to be limited to a discrete constellation. So in that sense, it is combination with modulation. Moreover, you can actually use a modulation. You can even use a constellation. So that doesn't prevent us from doing any of these. So as I said, we have a paper upcoming now on that. And what's the difference between task-oriented semantic communication and communication effectiveness layer? Okay, so this is what I want to, maybe this is one thing that I really want to convey, because as I said, I see a lot of papers, like more, for example, claiming, like this inference problems are actually the effectiveness problem. And for me, like task-oriented semantic communication is just joint source channel coding. So you have a task, whatever is the objective, you have some source, you want to reconstruct it, and then you have some measure of reconstruction quality, and that's what you want to optimize. And this reconstruction can be easily a class of that source, which is, in my opinion, is just a remote joint source channel coding problem, where the class is just a latent variable that we don't directly observe, but we want to convey. Now, in the case of task-oriented, the effectiveness communication, which I said, is that here, the goal is, we are communicating iteratively over many, many times. And the objective is a long-term kind of, this kind of discounted, for example, reward. So it's not important what we reconstruct or what we do at every action. So it's a much more kind of, so in a way, when I said initially, I said, a new way of kind of, the way formulating this effectiveness problem. But I said it's a partially new, because I was trying to say that there's actually a lot of literature on control with communication constraints, which is more or less the same thing. But that literature was more from traditional control perspective. So they were looking at the stability kind of properties under communication constraints, whereas our approach is more aligned with this modern Markov decision process and reinforcement learning way of looking at pretty much the same control problems, but like looking at the non-stationary kind of behavior with the communication constraints. So I hope that is kind of clear. Okay, and I think we can stop here. Thanks a lot, Deniz. Thank you very much. Thank you for also taking. Sorry for taking the extra time, but yeah. No, thank you for devoting the extra time, and thank you for this very informative and dense talk. So once again, I'd like to thank Deniz. Thank you. Virtually. Yeah. And before we all go, I just wanted to advertise next week's webinar, which is from Osvaldo Simeone. And it's going to be on Bayesian distributed learning and wireless systems. And it's going to happen next week, same time. So I hope to see all of you back here.